What if the material holding up every building, every bridge, and every road you have ever used was secretly one of the most dangerous things on the planet? Not because it collapses, but because of what making it is doing to the air we breathe. Here is the twist. The fix was never about inventing something new. It was about doing something differently with what we already had. And when a group of researchers in China figured it out, engineers across 4 continents dropped what they were doing and started paying attention. Before we go any further, if you are someone who loves discovering the technologies quietly rewriting the world, hit that like button right now, subscribe to the channel, and share this with one person who would never expect concrete to be this fascinating. Seriously, this one is worth sharing. Now let us get into it. Concrete is everywhere. That sounds obvious, but the scale of it is genuinely hard to wrap your head around. It is the second most consumed substance on Earth. The only thing humanity uses more of is water. Not oil, not steel, not plastic. Water, then concrete. Everything else falls behind. Every skyscraper that cuts through a city skyline, every highway stretching across a desert, every dam holding back a reservoir, every tunnel carved through a mountain. The foundation of nearly all of it is the same gray, ordinary material that has been mixed and poured the same basic way for over a century. And here is what makes concrete so hard to walk away from. It is not just common, it is brilliant. It is cheap enough for even the poorest countries to build with. It is strong enough to hold up structures that weigh millions of tons. It can be poured into literally any shape you can design. It does not rust like steel does. It does not rot like wood. It does not crack under normal pressure like glass. It hardens on its own without any special treatment. And once it sets, it can last for generations with very little upkeep. Civil engineers love it because after over 100 years of using it constantly, they understand exactly how it behaves. In heat, in cold, under stress. After decades of use, builders love it because you can find the raw materials almost anywhere on Earth. City planners love it because once it is poured into the ground, it tends to stay exactly where you put it. The entire profession of civil engineering was built on the assumption that concrete exists, that it works, and that it will keep working the same way it always has. It is not just a material. It is the backbone of modern civilization. So why is there a problem? The problem is buried deep inside the chemistry. And for a long time, nobody knew how to get it out. To make cement, which is the key binding ingredient that actually holds concrete together, you have to take limestone and heat it to over 1,400 degrees Celsius. That is not warm. That is not hot. That is the kind of temperature that makes rocks break apart at the molecular level. And when limestone breaks apart at that temperature, it releases carbon dioxide directly into the atmosphere as a chemical byproduct of the reaction itself. This is the part that makes the problem so stubborn. It is not about burning dirty fuel in the kilns. Even if every cement factory on Earth switched to perfectly clean, perfectly renewable energy tomorrow, the carbon would still come out. It comes from the stone. It is locked inside the chemistry of the process. You cannot engineer it away without changing the process entirely. And the scale at which the world makes cement is almost incomprehensible. The cement industry alone, not all of construction, just the cement making part, produces roughly 8% of all the greenhouse gases that humans release every year. That is more than every commercial flight on every airline on every route on the planet. It is close to matching every single car and truck and bus driving on every road across the entire world. 8% from one ingredient in one material that almost nobody thinks about. For years, researchers tried to find workarounds. Some replaced portions of cement with industrial byproducts like fly ash, the residue left over from burning coal or slag from steel production. Others developed entirely different chemical mixtures called geopolymers that skipped limestone-based cement altogether. A few built carbon capture systems directly at cement plants to trap the emissions before they escaped into the sky. All of these helped a little. None of them changed the fundamental math enough to matter at a global scale. The world kept pouring more concrete than ever. Emissions kept it climbing. And the core process, mixing the ingredients, pouring the slurry, waiting for it to harden, stayed almost completely unchanged. The question nobody had seriously asked yet turned out to be the right one. What if the problem was not what goes into the concrete? What if it was what you do to the concrete the moment it comes out of the mixer? That question led to something engineers are now calling compression casting, or CCC. And the answer it produced was not what anyone expected. Fresh concrete, right after you mix it, is not solid. It is a thick, wet, heavy slurry. It is full of water. It is full of tiny trapped air bubbles. The particles of cement and aggregate, the crushed stone mixed in to add bulk and strength, are loosely packed together with gaps between them. Normally, you pour the slurry into a mold, run vibrating tools through it to help settle the particles a little, and then you wait. Gravity does most of the work. Time does the rest. Over hours and then days, the chemical reactions proceed. The water gradually works its way out, and the material slowly transforms into solid concrete. This process has not changed in any meaningful way since concrete became the dominant building material of the modern world. It is just how concrete works. Everyone accepted it. A research team spread across 3 of China's most respected technical institutions: Tongji University, the China Building Materials Academy, and Shanghai Jiaotong University decided not to accept it. They asked what would happen if, instead of waiting for gravity and time to do the work, you applied serious mechanical pressure to fresh concrete while it was still wet. Not a gentle squeeze, real force, between 5 and 15 megapascals, which is roughly the kind of pressure generated inside a heavy-duty industrial hydraulic press. What happened inside the material when they did this was dramatic. The particles were forced together so tightly and so quickly that excess water and trapped air had nowhere to go. They were squeezed out. The concrete became dramatically denser almost instantly. Think about the difference between picking up a loose handful of dry sand and picking up a compressed block of sandstone. Both are made of the same material, but the structure is completely different. The porosity of the concrete, the percentage of the total volume, made up of tiny internal gaps and voids, dropped by around 45% compared to standard concrete made the same way. And that single change had consequences that rippled through almost every weakness concrete has ever had. Those voids are where concrete's problems begin. Nearly every form of long-term concrete damage traces back to them. Cracks start at voids because voids are points of structural weakness where stress concentrates. Water infiltrates through voids, carrying with it road salt, seawater minerals, and chemical pollutants that travel through the material until they reach the steel reinforcement bars embedded inside. Once those chemicals reach the steel, they cause corrosion that slowly destroys the structure from the inside out, invisibly over years or decades. Freeze and thaw cycles, common in any climate with cold winters, are destructive precisely because water gets trapped in voids and then expands when it freezes, breaking the material apart from within. Reduce the voids by 45%, and you are not just making slightly better concrete. You are systematically addressing the root cause of most of the ways concrete fails. But the most significant discovery was something even more specific. Inside every piece of concrete, at the microscopic level, there's a boundary zone where the cement paste surrounding each piece of aggregate stone comes into contact with the stone itself. In standard concrete, this boundary is actually the weakest point in the entire structure. The cement paste right at that interface is looser and more porous than either the paste or the stone on their own. It is where cracks almost always begin when a concrete structure is under stress. It has been a known vulnerability for decades. Engineers have simply learned to design around it. Under compression casting, this boundary zone tightened significantly. The voids in that interface dropped by up to 35% compared to conventional concrete. The weakest link in the chain got measurably stronger. The numbers that came out of the lab testing were the kind that make structural engineers read the paper twice to make sure they understood it correctly. Compressive strength, the ability of the material to resist being crushed, increased by more than 80% in the highest. Pressure test batches. Resistance to water intrusion improved substantially. Resistance to freeze and thaw damage improved substantially. Resistance to chemical attack improved substantially. And the researchers achieved all of this without changing the recipe at all. No expensive additives, no exotic new materials, no reformulation. The same cement, the same aggregate, the same water, the same ratios, but just handled differently for a window of time right after mixing. Now pause here and think about how big that is. You did not make a better concrete by inventing better ingredients. You made a better concrete by doing something different to the same ingredients you already had. That is a fundamentally different kind of discovery. If you have made it this far, you clearly care about the ideas that are quietly changing how the world is built. So here is your moment. Drop a comment right now with the word concrete. If this is blowing your mind, hit the like button if you think more people should know about this, and subscribe so you catch everything else we're putting out. Your engagement genuinely helps this reach more people. Now back to the story, because this is where it gets even more interesting. The research team did something else that was almost as significant as the discovery itself. They published everything. Not a summary, not a press release. Every data point, raw spreadsheets, microscopic images, taken at extreme magnification showing the internal structure of the material under different pressure levels, force and displacement readings from nanomechanical tests that measured the strength of the material at the scale of individual particles. All of it freely available for download. Open license, no paywall, no proprietary lock. In an industry where companies routinely guard their methods and where academic research often sits behind expensive journal subscriptions, this level of transparency was almost shocking. And the reason it mattered so much is that it meant any engineer anywhere in the world could download the data, check the methodology, run their own tests, and verify whether the results were real. In science, that is how extraordinary claims earn trust. Not by being announced loudly, but by being tested independently and surviving. They survived. And when international engineers started replicating the findings, the conversation shifted from academic interest to industrial urgency. But the concrete story is only half of what happened in 2025, because while compression casting was working its way through research journals, a completely different technology was developing in parallel that was asking an even more fundamental question. What if some buildings did not need that much concrete at all? The technology is called B-Core. It was developed by Broad Group, a Chinese construction company that has a long history of doing things that most people in the industry assume cannot be done. In the early 2010s, they assembled a 30-story hotel in 15 days using a modular construction system. The industry watched, was impressed, and mostly moved on. B-Core is what came next. The panels themselves looked deceptively simple from the outside. 2 thin sheets of steel, one on each side, held apart by a precisely engineered lattice of hollow steel tubes arranged in a geometric grid. If you cut one open and looked at the cross-section, it would remind you of the inside of a waffle. Iron, but built to tolerances measured in fractions of a millimeter. The engineering logic behind it was borrowed from aerospace. Aircraft fuselages are thin. They weigh almost nothing relative to their size, but they are extraordinarily strong because they distribute stress through their structure rather than absorbing it through sheer mass. B-Core panels work on the same principle. The outer steel skins handle tension and compression. The internal tube lattice handles bending and twisting. Together, they create a panel that weighs less than a tenth of a comparable reinforced concrete slab while carrying similar structural loads. The implications for construction speed are profound. The panels are designed to connect to each other using robotic fasteners, which means an entire floor of a building can be assembled in hours rather than days. In 2025, a 10-story building in Chengdu was put together using B-Core modules in under 30 hours. The workers were not rushing. The system is simply designed for that speed, in the same way flat-pack furniture is designed to be assembled without special tools. The speed is built into the geometry. But the most strategically important advantage of B-Core has nothing to do with speed or cost. It is about earthquakes. Buildings in seismic zones face a physics problem that has never had a satisfying solution. Concrete structures are heavy. When the ground moves, all that mass has to go somewhere, and the forces involved can be enormous. Engineers have developed sophisticated systems to manage this, but the fundamental challenge of a very heavy, rigid structure sitting on shaking ground never goes away. B-Core panels weigh a fraction of concrete. Lighter structures respond to seismic forces differently. They absorb and redirect that energy in ways that heavy concrete frames simply cannot. Testing showed B-Core panels handling shock and vibration with a resilience that conventional concrete structures struggled to match. In the regions of the world most vulnerable to earthquakes, which include some of the most densely populated places on Earth. That is not a minor technical footnote. It is a life safety difference. Now consider what happens when you put these two technologies together. Compression casting makes the concrete that does get used dramatically stronger and dramatically cleaner. B-Core reduces how much concrete a building needs in the first place. Together, they attack the problem from both directions simultaneously. Stronger material, where you need it, less material overall. The combined effect on construction cost, carbon output, weight, and long-term durability is significantly larger than either technology delivers alone. That combination is exactly what triggered the response from the global construction industry that followed. Construction is not an industry known for moving quickly. Building codes take years, sometimes decades, to be updated. They are deliberately slow because the consequences of getting a structural calculation wrong are not measured in dollars. They're measured in human lives. Large companies move cautiously. Regulators move cautiously. The entire system is designed around the principle that proven and tested is far more valuable than new and promising. So when serious international interest in these technologies started accelerating within months of the 2025 publications, it was a meaningful signal. Not marketing, not hype. Actual engineering investment. 34 international patent families now cite the original Chinese research directly. The filings come from Germany, Japan, South Korea, and the United Kingdom. These are not academic citations. These are companies and research consortiums committing legal resources and capital to the technology. By 2026, China had exported over 12 million metric tons of carbon-cured concrete additives to the United States, the United Kingdom, and Southeast Asia. That represents a multiple-fold increase compared to just 2 years prior. Lafarge-Holcim, one of the largest cement producers on the planet, signed a 5-year licensing agreement with Beijing Cement Group to adapt B-Core technology for European prefabricated construction. In Germany, a research consortium ran compression cast trials on a real highway project outside Berlin. Japan's Obayashi Corporation launched a joint research program with Beijing University of Civil Engineering, targeting significant cement reductions for construction tied to the Osaka Expo. South Korea's Hyundai Engineering announced plans to build a domestic B-core panel manufacturing facility as part of its Smart City program. None of this is idealism. It is economics. In markets where carbon emissions are taxed or capped, a 40% reduction in cement use translates directly into lower costs and lower regulatory exposure. Cutting the price of your most expensive raw material while simultaneously making your product stronger is not a trend you can watch from the sidelines. It is a competitive shift that no serious company can afford to ignore. The real-world validation that preceded all of this corporate activity was critical. On the Pingjiang River, 150 meters of bridge deck built with compression cast concrete was monitored continuously for 12 months using embedded sensors, measuring strain and moisture throughout the structure. The compressive strength recorded from the in-place material averaged 61 megapascals, matching the laboratory predictions almost exactly. 0. Visible cracking. Stable moisture readings throughout. Every data point from that year of monitoring was archived publicly, available to any engineer anywhere to download and analyze. In Shanghai, prefabricated B-core adjacent wall panels installed in a pilot housing project showed a 15% improvement in thermal insulation compared to conventional panels and required significantly fewer post-installation repairs. The engineers who chose the material were not motivated by environmental branding. They chose it because the data showed it was stronger, more efficient, and less expensive over the full life of the building. This is what separates this moment from all the previous moments when people announced that concrete was about to fundamentally change: open science, independent replication, real-world results, and real structures. A clear economic case that makes adoption rational, even for decision makers who do not care at all about climate. The claim has receipts now. You can read them yourself. So how large could this actually become? The life cycle models built by researchers suggest that switching just 30% of all new structural concrete worldwide to the compression casting process could reduce global carbon dioxide emissions by approximately 850 million tons per year. To put that number in perspective, it is more than the total annual emissions of Germany from every power plant, every factory, every vehicle, and every farm combined. One process change, applied to less than a third of global concrete output, delivering that kind of climate impact. But turning a proven technology into a true global standard is a long road, and it is important to be honest about where that road becomes difficult. Building codes in most countries update on timescales of years to decades. Every country that wants to adopt compression casting at scale needs its own independent testing to verify results under local soil conditions, local temperature extremes, and local regulatory frameworks. It needs its own approval process. It needs a trained workforce that knows how to operate the equipment consistently and correctly, because the quality of the output depends heavily on the consistency of the pressure applied during casting. China can publish the method openly. The rest of the world still has to do the work of adapting and certifying it locally. There's also the infrastructure question. Compression casting requires equipment that most existing concrete plants do not have. Retrofitting facilities or building new ones requires capital investment. For major construction companies in wealthy markets, that investment likely pays back quickly through cost and regulatory savings. For smaller contractors and builders in developing economies, particularly in the regions of the world that need affordable lower carbon construction most urgently, the barriers may be significantly higher. These are real constraints. They do not change what the science demonstrates. They define the gap between what is technically possible and what will actually happen at scale and at speed. Closing that gap is a policy challenge, an investment challenge, and a coordination challenge as much as a technical one. The researchers in China gave the world a tool in 2025. Whether the world picks it up fast enough to matter in the time frame that the climate situation actually demands is a question that science alone cannot answer. What is clear, for the first time in a very long time, is that the fundamental process of making and using the world's most consumed building material is actually changing. Not at the margins, not only in a laboratory, in real structures, real bridges, real buildings, real infrastructure that real people are using right now. That is genuinely new. The last time the core logic of concrete changed in any significant way, it reshaped the physical landscape of the entire planet. Every city you have ever visited, every tunnel you have ever driven through, every dam holding back water that powers a city's electricity, it exists in its current form because concrete made it economically and structurally possible. We are at the beginning of the next version of that story. The material that built the modern world is being rebuilt itself, and the ripple effects of that change on cities, on climate, on the economics of construction in every developing country, still building its infrastructure from scratch, are going to be felt for decades. You just watched a video about concrete. And if you feel like that was actually one of the more significant things you have learned this week, that is exactly the point. The technologies reshaping the world do not always announce themselves. Sometimes they are hiding in the most ordinary thing you walk on every single day. If this video shifted how you see something you have walked past your whole life without a second thought, here is what I want you to do. Like this video. Not for the algorithm, though that helps too, but because it tells us this kind of deep dive storytelling is worth continuing. Subscribe if you are not already here. And leave a comment answering this. If a breakthrough this significant was sitting right in front of the engineering world for decades, what other obvious solutions do you think are hiding in plain sight right now? Biggest problems, simplest possible answers. Let us talk about it below.